All right, line P1, learning task number 9. We're going to take a look at multi-winding and tap transformers. And this one's going to be more about the purpose and the theory behind them. The next learning task is going to be where we're going to start to deal with the actual calculations that we are going to have with them. But a multi-taps transformer is a really common thing, and usually what it's been placed in there for is for compensation. Over here, we are showing a circuit that has got some line drop off of it. And line drop is where we've got the resistance of the lines itself that is going to go and cause some sort of a voltage drop over top of those lines. If I were to go and take a look at this, I see that I've got on my primary side over here 2400 volts, but then I've got 0.3 of an ohm, which is relatively small. You know, there's not a lot of resistance that we have inside there. However, if I'm passing 200 amps through there, I'm going to go and end up with a voltage drop off of this. If I go and take 0.3 of an ohm over here, multiplied by 200 amps, it's going to go and tell me the voltage drop that I would have here. We call this the IR drop. It's a common thing, you know, you can talk about the voltage drop on the line, but more commonly you can hear about the IR drop because it relates it to the amount of current that we are pulling through at any given time. We'll take 0.3 times 200, which gets us to a value of 60 volts that we would be dropping across this line over here. So from source all the way over to transformer, I'm going to be dropping 60 volts on that line, and I'm also going to be dropping another 60 volts on this line. It's got the same resistance, the same current that is going to be going through it, which means that 60 volts plus 60 volts is 120 volts, which means that this 2400 volts that we have is actually going to be 2400 minus $1.20, which leads us to really just having a series circuit now, 60 volts, 60 volts. What we must have left over here, according to Kirchhoff's voltage law, would be the remainder, which in this case is going to be 2280 volts that we will have over here. That 2280 volts is going to get passed through this transformer. Now, the transformer itself is rated as being 2400 to 240 volts, which means that it is a 10-to-1 transformer. If I would take 2400 divided by 240, you get 10. So if it's 10-to-1, that means that whatever I have on this side is going to go and be 10 times smaller than what I would have on this side here, the primary side. Which means that 10 times smaller is going to be 228 volts. 228 volts is what I would have for my output over there. It is not what we want to have out. We want to have 240 out. Instead, we're ending up at this 228. So we've had a little bit of a voltage drop that's happened inside of here. To compensate for that, it would be nice to be able to go and adjust what we have on this transformer. It would be really nice if we could somehow change the turns ratio that we would have inside of here. So instead of going down from 10-to-1, we would go down on a smaller ratio, which would mean that we wouldn't end up quite as far down inside of here. Now, this is a really common thing in seasonal type of industries. Let's say that you are working for a store, it's like a large grocery store or something like that. During the winter, they are going to go and have a lot of free cooling that's going to be taken care of. They have to still heat, but most of that's going to be done with gas. But during the winter, all of their massive drive-in type of freezers and refrigeration are going to, you know, not have to take as much power because it's cold outside, so they're not having to go and remove as much heat. But during the summer, all of a sudden you would have to go and have a lot more refrigeration active. And so what happens is during the summer, oftentimes what happens is we are going to go and increase our current. You know, this situation that we're seeing over here could also go and change dramatically based upon the amount of current that I'm going to be passing through here. Right now it's 2000 amps. That might be their summertime load when they're running all of the refrigeration. But during the winter, this grocery store might only be running, 1,000 amps, which would mean that if it was 1,000 amps, these, because it's a 10-to-1 transformer, would be at 100 amps. 100 amps. And if we have 100 amps there, 0.3, we'd be dropping 30 volts off of each of these, which means that we would be down to only a voltage drop of 60 volts off of here. So we would be at 2340, which would mean that by the time I carry that voltage back across here, would be just 234 volts. So we see that during the winter, during an unloaded season, as we would normally call this, we're going to be sitting with a higher voltage. But then as we load up inside of here, we would start to drop that terminal value of voltage. There are going to be customers, some of you are going to run into, that are going to run seasonal types of loads. They're going to go and have, some stuff that is just going to be, particularly in places that run refrigeration of any sort, they're going to be heavily loaded in the summer as they're stripping out that 30-degree heat from the air and, you know, releasing that to the atmosphere. It's a lot of work on those compressors. It's a lot of amps that are going to be taken out of it. But in the winter, all of a sudden, their voltage is going to change. So in some cases, part of your yearly electrical service in some of these plants is going to be changing your transformer taps, you know, leading into hot weather and then coming out of it, you know, again in October, November, something like that. Otherwise, you end up with too high of a voltage off of there. What we will have on those type of transformers is we are going to go and have percent taps. And the lovely thing about percent taps is simply that they are going to go and tell us, hey, what is my incoming voltage that I am going to go and have, you know, based upon the amount of line drop. So what we do when we are monitoring these is, let's say that I've got a customer that's getting a low voltage out over here on this side, and he's got those two lines that are being fed in. I'll let you draw them in here with just proper lines a second. So that's the incoming lines. Over here on this side, I know that I'm getting too little voltage out. Usually the taps are going to go and be on the high voltage section. Why? Because the high voltage section is going to have smaller amounts of current, right? And smaller current connections are easier for us to deal with than large current connections. Otherwise, you have to worry a lot more about heat and, you know, transformers, conductor size and everything like that. So usually we change on the high side. What we'll do is we'll measure with our voltmeter. So I'm getting the customers telling me things like, hey, I've got machines that are starting to stopping randomly. Sometimes my computer is glitching out. A lot of these are, you know, signs that the voltage is drooping too low and, you know, low voltage protection is kicking in on a lot of industrial equipment. So I see my voltage is too low over here. I can go and take a reading off of this side over here. Let's say that I am getting a reading of 220 volts out. If I'm getting 220 volts out and I know I should be at 240, all I need to do is find out what percent of that 220, or what percent that 220 is of what my rated is. So my actual over top of my rated is all I'm going to go and do. 220 divided by 240, which gets me to a value of 91.6. I'm coming in at only roughly 92%. So what I'm going to want to do is I'm going to want to move my taps to that because that's the percentage of volts that I'm currently at. So I will just take this, I will disconnect it from there, obviously power off, locked out, tag out, everything else like that. Don't be an idiot. We want to keep you all alive. And then once I've got it all locked out, open that up, I will move this thing down to this section right over here. And that's going to be my transformer tap. And then when I run this, now I'm going to be at a 0.95. But what I'm going to see is I'm going to go and see a boost. I won't be getting the full 240 out, but I'm going to be sitting a lot higher than this 220. We will calculate those ratios on the next one. But all it is just a simple little bit of math that you're going to do where you're going to say, what is it rated at? What am I at? I'm going to go and move this because if it's operating, you know, I'm getting it 95%, then move it down to the 95% voltage tap, which will bring this thing up. What it is actually changing for us is it is changing the volts per turn, right? What I have up top here, this, you know, 2400 volts or whatever it's going to be, I guess it would have been 2200 volts with all my line drop. The 2200 volts, I had it over top of 100% of the turns. Now I'm going to drop it over top of 0.95 of the turns, which means that we have got a lot more volts per turn that are going to be induced onto the secondary side. Two main types that we are going to go and deal with. We are going to go and have no-load and on-load tap changers that are going to be applicable for places that need to change taps a lot. Some places, they don't want to have to go and call in an electrician every time to go and operate that. They might want to just get their plant millwright to do it. If they do have the plant millwright that is going to be making those adjustments, they'll want to place on a tap changer. Now, an on-load tap changer obviously is going to be able to change the taps while the load is still on. They don't need to go into a shutdown, and no load tap changer is going to be cheaper, smaller, easier to work with, but you have to shut everything down, click it over to the next position, and then turn that thing back on. If you don't have one of those tap changers, the only other method would be for you to go and actually open up the transformer and select and clean off the high voltage taps. Let me show you a picture of that. All right. This is the insides of a multi-tap transformer. There's a bunch of terminals down here along the bottom. It's an older transformer, it's in use, but this is what they look like on the inside. Terminals are all going to be along the bottom, and then these over here are going to go and be my individual transformer taps. And if I go and just zoom in here a little bit, what you'll notice is that there is a lead that comes off of one of these over here. This right over here is going to go and be a transformer lead that is going down, and it's making connection with one of my lug sets. I can see it coming down to this one over here. This is going to be one of my high voltage lug sets that I'm then going to go and pass out to my outside wiring over here. The rest of these over here are simply just parts of the transformer winding. It's a flat type of winding that has been taken and then bent out and then pushed back in, and then wrapped around and taken and bent out and pushed back in, and they provide connection points. The way that these taps are changed is that you are going to have to obviously take power down and lock out, tag out. Then you're going to go and pick the correct tap. They should have identifiers on them. There's usually just going to be a transformer legend. They won't necessarily say it directly on these. And you're going to have to clean off the varnish. So you're going to have to go and there's going to be a little bit of paper wrap sometimes around them that you're going to scrape off carefully with a utility knife. Then you're going to sand that down until it's nice and smooth. Fine grit sandpaper. You want to take all the varnish off of it. And then what you'll do is you will unbolt this. It's just a through bolt that's going through there. And then you're going to take that flexible lead and you would go and bolt it through onto here. But the big thing with these ones is that you need to clean off all of that varnish. I have run into it in the field before where people have changed taps, and because the varnish is clear, they just assume that if it's clear, electricity can pass through it because the electricity can see it or something like that. I don't know what's going on really with those people, but whoever changed those taps left the varnish on there. They cooked off the transformer. It was a crappy business trying to go and replace that transformer too later on. But anyways, just make sure that you are cleaning those taps off when you move them over. Now you see that this is obviously going to go and be beyond the scope of most of our millwrights. It's something that the electricians should be doing, or you as the plant electrician should be doing. If you are doing this, it is going to be, once again, a time-consuming thing. The other thing is, when you open these up, a lot of our transformers are going to be wound with aluminum because it's lighter and it's a good conductor. Nothing wrong with it. So if we're winding with aluminum, that means that we need to go and protect the aluminum as well. We have to go and put on our antioxidant and things like that. All right, I'm going to go and jump back into these over here. Now that we've seen what one looks like on the inside, that is the taps on the transformer. In a lot of cases, going and adjusting these inside the transformer can be a lot of work. So what we will do is we will move to an on-load or a no-load type of tap changer. We're going to look at both of them, but really what these on-load and no-load tap changers are going to do is they're going to take an individual lead off of every single one of those taps. In other words, when you initially install this, you're going to take a lead from here to the on-load, a lead from here to the on-load, a lead from here to the on-load, a lead from here. You're going to take 6 leads for each of these windings. This is a 3-phase transformer. It's just the best picture that I had of, decent-sized taps that we could zoom in on here. But what you would have to do is you'd have to take a connection from each one of these out to that tap changer so that then the tap changer can change it outside of the transformer. Going back into this, my no-load tap changer over here, the transformer, once again, mounted somewhere over here, and from each of those individual winding sets, we've got all of those, we are going to go and have one of those that's going to be coming back to here, sorry, we shouldn't go there, to here, etc. They're showing it just as a simple schematic down here in the bottom, but every single line is brought out. These are not designed to go and operate during load, whenever we are carrying actual load. If we are carrying load, it's going to arc out because these are just, there's nothing that's fast about the action of these. It's going to be a big, massive crank handle, and it's really only going to move as fast as you crank this over from place to place to place inside of here. What we will do is we will go and slide from one component to the next, and it's going to go and make connection. Let's go and take a look right now. We have got this line that is connected over here, as well as we have got this line that is connected over here. So if I were to go and follow my total lines in all the way through, so we're just going to say this is my source voltage. The voltage doesn't matter much right now, but it's the high voltage side because it's got more windings, and therefore it's the low current, which means it's easier to go and switch out. I can take a look and I can see I'm going through 1, 2, 3, 4, up and through, then my current path completes through here, and then goes 1, 2, 3, 4, 5 on this side, and back out to my source value of voltage. If I were to go and move this tap changer, what it's going to do is it's going to go and change my tap value. Let's take a look. I'm just going to draw over with blue so that we can compare, the red path that we're currently in over here to the blue path. These are just going to be the positions. You have a little arrow on here that say you're in position number 4, or something like that. If I change it over to, let's change it over to position number 5. In position number 5, I would have this winding over here, and I would still have this same one over here. So if I were to go and trace through using the blue, 1, 2, 3, 4 on that one. So that number of turns has not changed. But then coming through to this one here, now I'm going 1, 2, 3, 4 on this one over here on my way out. If I compare it, what I have on the red was I had 9 turns. They're representative. There's obviously many more turns inside here than 9, but they're drawing them as 9 inside of here. And then compare that to the blue. The blue has got 8 turns. What is this going to do? This is going to go and change, once again, my volts per turn, right? If I have got, let's say that on this side over here, that this 8 turns represents actually 80 turns. It would just be easier for us to up that. We'll multiply it by 10. This one here would go and represent 90 turns. And if I go down here to the bottom side, we're going to say that this bottom side over here has got 10 turns total, okay? If we were to go and take a look at our value of voltage, whatever we place across here, let's go and place 590 volts across here. If I do 590 volts over top of 90 turns, I'm going to go and end up with 590 divided by 90, which gets me to a value of 6.55 volts per turn, which means that on the output side, I would have 65 volts, 10 turns, right? 10 times that same 6.55, so I'd end up with 65 out on the 9 turn. I'll just write that down there, 65 out. Obviously, this is not a useful voltage. We're just doing this to go and show the way that the voltage changes. For the other one, if I move to the 8 turn over here, we would have the same source voltage of 590, but now it's over top of 80 turns. So let's go and do that. 590 divided by 80 gets me to a value of 7.37 volts. So if I take that 7.37 volts, put it over top of the 10 turns I have on the secondary, we would see that we would go and get a 73.5 volts that we would have out. And so we see that us changing the turns does nothing to go and change this value that we have up top over here. Sorry. This value. What we're feeding into the transformer does not change. All it's doing is it's changing the number of volts per turn that we're going to be dumping on the output side over here. We move it to, position number 5, and we found that inside of position number 5, we were seeing, a higher amount of voltage that would be out of this one. And as we move to position 4, we get a lower output. As we move to position number 3, it's going to introduce another turn, so it's going to get lower, etc. as we go through these. All right. You should be able to analyze one of these, to the extent that you would be able to tell me which position I'm going to go and get my highest value of voltage out or my lowest value of voltage out, because that shows that you've got the theory down pat for, how it's adjusting the volts per turn off of them. For a on-load tap changer, they're a bit more complicated, and they're going to go and incorporate a sliding contact. Now, it could be circular sliding. They're showing it in a linear fashion over here, but it could absolutely be a brushed contact on a circular commutator that would work off of them. In fact, most of them are. What they do have inside of it is they are going to go and have a common core inductor over here. Now, what does an inductor do? An inductor opposes any change in current by using its magnetic flux. But the problem is over here, I'm feeding into the center of that inductor, and I'm passing some current through in that direction and some current through in that direction over there. And when I do that, that is going to go and counteract my flux. My flux over here is going to counteract each other. And if the flux counteracts and cancels each other out, the amount of counter EMF that I'm going to build off of this is going to be 0, right? EG is equal to VLV. The voltage generated, the counter EMF across the inductor, is based upon the amount of flux. And if I've got no flux, I've got no volts. So I'm not going to drop anything over top of this inductor. The inductor is going to act as if it were just a couple of loops of wire inside of there. We only are going to see the resistance. So I'm going to take all of my current, it's going to split across these two evenly because they're equally sized, and then it would go through all of these windings over here. That's going to be my incoming, my high voltage side. When I go and operate it, what's going to happen is that for a split second, we're going to be bridged across. So for a split second, as this thing is moving up off of here, this first point over here would obviously lose contact. All the current would be flowing through here for a split second, and then the next instant we would be bridged across over here. At this point, we have got two separate paths for current flow. We're going to go and have this current flow that is going to go and be my main current flow. That's going through here. That's what we're transforming. And at the same time, because we have got current flow that is traveling through there, that current flow is going to be fluxing out our core. And as it fluxes out our core, it is going to generate a small value of voltage across these windings over here, right? We've got a certain number of volts over top of these turns. Therefore, these ones here are going to go and pick up the same volts per turn that is going to be generated across them. What do they have to drop it across? Well, the only thing that they can go and drop it across would be across this reactance. But I see that at this point, now I am going to go and have no counteracting, no cancellation of that flux. So for that split second, and guys, this is really happening like done like that. These things operate, they sound like a gunshot when they go off. It's just a bang as they move over from one to the next. But what's happening is just for that split second, I'm going to go and have my current that is going to go and travel through that loop. This inductor is going to go and act and give me the voltage drop that would be necessary so that I don't accidentally short these out. If I didn't have these inside here, if this was just a straight bar, the instant that I slide across here, all of that flux that is being generated inside here that's fluxing this is just going to go and cause a massive, massive explosion when I short over top of it, because now it would have voltage over top of 0 ohms of resistance. That's why we need this coil inside of here. And then in the next instant, it moves all the way up to here, and at that point, our current splits, cancels the flux, and the inductor coil itself gets, ignored. Once again, we just see the resistance of that inside of there. It is going to operate incredibly fast. What it's going to have is it's usually going to have a massive spring. We're going to have motor windings on there. The motor is going to go and coil the spring, and then there's going to be a sear that's just going to go and release, and it's just going to drive this thing over from place to place inside of here. Move it up, move it down, etc. There's going to be time in between each one. There's going to be this like boom as it moves over, and then it has to wait, recoil the spring, and then boom, you can move over to the next tap, etc. It is super fast, but it does not beat the speed of electricity, right? And electricity is moving at epsilon naught. It's moving speed of light type of speeds that we have out of it. So we're not beating it by our, couple millisecond switching that we're having. That's why we need to have this inductor in there. That being said, this inductor is only acting as a voltage drop for a couple of milliseconds. And after that, it's taken out of the system again. So it doesn't need to be overly built because it doesn't have to dissipate a lot of power, a lot of heat, because that's only happening for a split second. All right, all of these tap changes that we see over here, the no-load and the on-load tap changers, are going to be generally used inside of important, heavy, pricey types of industries. This one over here, the on-load tap changer, is usually going to be utilized by BC Hydro. They have got a ton of these on-load tap changers that are going to be consistently switching and watching what we have got on the grid. When there's too many people running their AC in the summer, BC Hydro on their transformers are going to start firing these things over, moving these things up so they get more volts per turn across their transformers, and then they'll move them back down. These other ones over here, the no-load tap changers, these are much more common inside of important industries, but where it's not critical. It's just going to be an individual business. It might be a multi-million-dollar business, and they might have to go and do this, once or twice a year. But most of these big businesses are going to go through shutdowns, right, where they will go and do a maintenance shutdown, and a bunch of stuff happens. So as long as they time those shutdowns for the shoulder seasons, they're going to be able to go and do the complete power off, change it over with no problems whatsoever. And even if it was the middle of the season they had to change it, they would have to shut down, which sometimes can be a bit of a process, but the actual operation only takes, a couple of minutes for somebody to go and move this over. These ones, by the way, usually are going to go and have a manual handle, and you will bolt the handle in place. Because what you don't want to have happening is, the apprentice millwright walks by and says, what does this handle do over here, right? It's always a bad time to go and, just test what something does on a job site. Oh, who was it? Hold on, just make me think of the story here. Never mind, I won't tell you because but a former student of mine was working in a bank, and they pressed a button just because they were standing next to their journey person, and they just kind of standing around there. They were getting instructions. I think it was actually a credit union, but they're still a bank. And they saw a button on the wall, and they pressed it. They triggered the silent alarm. I had no idea what would ever possess anybody to, press an unlabeled button inside of a bank. But yeah, the thing went into shutdown and alarms, and the police showed up, and it was a huge, massive issue. It's a dumb thing. Just don't operate stuff if you don't know what it's going to do.